Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, things happening inside the universe, how things interact, how things evolve, everything going on inside the universe. It's a great topic. I love being a scientist. I love being a cosmologist. It's really cool that I get paid to unravel the mysteries of the universe, though most of the days I'm just unraveling the mysteries of why my codes don't work. But approximately same thing. So yeah, I love being a cosmologist and being a scientist in general and chatting to everybody about all of the cool things I get to study and get to work on. And as you might notice, I'm very easily distracted today. There's just like a fly that caught my attention and some buttons at the beginning that I was having issues with. Been away for 3 weeks and suddenly everything feels different, but it's good to be back. Glad to see all of the regulars. Hey, Ange, Beth, Paul, great to see all of you coming in. As always, welcome back to any regular viewers. Welcome if you're a first-time viewer. If you haven't done so yet, please do like, subscribe, leave a comment, do all of the usual YouTube things that boost engagement. I really appreciate it. Press all of the buttons. No sound. So no sound for Scott. If someone else can confirm if there's sound, please do let me know if sound is working, or if it's just on Scott's end, or if it's on my end. Of course, if there's no sound, you're not going to hear this. But I'm guessing other people would have shouted by now if there were not any sound. Anyway, David Dunn, Scott, Kimmus, great to see everyone here. Chris, nice to see you again. So if anyone doesn't follow Chris Patterson here, make sure you follow Chris on YouTube. He has an amazing YouTube series with some very, very cool videos and was a one-time guest on Cup of Cosmology as well. We had great fun talking about random topics. You all hear me well? Okay, great. Then it's on your end, Scott. Sorry. Thank you, everyone, for confirming that sound is indeed working. So yeah, I'm a theoretical physicist. I study cosmology. I study the cool stuff happening inside the universe. And this is an interactive stream. So the idea here is that you can ask me anything you want about cosmology, about science in general, about physics, about what it's like being in academia, about conferences, about basically anything you want. This is what the ask me anything means. It's just you can ask me anything you want. Of course, if you ask me personal stuff, I may or may not answer depending on what you ask. But the idea is that you can ask me anything you want. And as always, I see that Paul is ready here with a question. I love that you always have a question ready for me, Paul. Thank you. So before I get into questions, just want to say I've been away for 3 weeks, been doing a lot of things, actually. I managed to do like 5 different things, 4 different countries, nearly 2,000 kilometers by train, a couple of flights, and God knows what else. It was an intense couple of weeks, and I basically crashed this weekend because I'm so tired from the last busy couple of weeks, and I've had a relaxing weekend, and now I'm good to go and energized and ready to chat to you all again. But long story short, it is great to be back. I'm happy to be back on Cup of Cosmology, and now I'll be back semi-regularly until my next travel, which is in 3 days, and then again in 3 weeks. But for now, Cup of Cosmology is back more or less regularly. What's today's agenda? Don't have anything fixed. I did not want to prepare a topic today because, as mentioned, tired, see above. So today's agenda is wherever you want to take this conversation, that's where we're going to go. So whatever your questions, that will dictate the mood of the show and where we go and what we talk about today. As always, you can ask me anything you want, and then we'll move the conversation along from there. Already you see a long question from Paul here. Let's go to that. Just a comment from Kimmus here, because I see a name I remember. I learned that recently at the PhD defense of Kunter the Kant, a very nice person who just defended 2 days ago, former colleague of mine, that the data collected by Gaia recently point towards the absence of dark matter in the Milky Way. What do you think about this, huh? Well, that's interesting. Let me get to that one in a minute. I just got distracted by the name of a colleague, but first let me go to Paul's question here. Is entropy an input for long-term models of how the universe will evolve, or is it an output, such as we model the universe and see what happens with entropy? So, yes and no, both, neither, all of the above. Entropy tells us basically how energy moves in the universe or in a system in general. The idea behind entropy is, entropy is the amount of chaos you have in a system. Entropy always increases. This is something that appears in our models because the laws of thermodynamics are assumed. So when we have, for an example, computer code that simulates the evolution of the universe, what we're actually simulating is the evolution of the components of the universe and of space-time itself if you're doing that type of physics. good type of physics as well. So then you put things like dark matter and the standard model particles and dark energy, and all of these things are treated as different types of fluids or gases because it's kind of easier to treat things as a fluid. Like we can just say, normal matter behaves as a fluid in the cosmos. And then you need certain laws on how these fluids behave, certain assumptions on how these species behave. And for that, we do rely on the laws of thermodynamics, which are things that are pretty well established. We know how entropy behaves. We know how entropy should act. So this is something that you can put into your cosmology. Is like, okay, laws of thermodynamics are something that is well tested and should not change whether you're doing them here or up there or wherever you do them. We have checked that this doesn't change. So what you can do is, and what we do is, we assume certain thermodynamical laws are obeyed. If we are treating something as an ideal gas, we assume that it behaves as an ideal gas and follows laws of gases in that they're going to expand to fill their space and stuff like this. So entropy is not really an input or an output. It's an assumption, or it's not, entropy itself is not an assumption, but the laws of thermodynamics as we know of them are used to derive the equations that then tell us how things in the universe behave. What you need to know is how different things behave. Like, does normal matter behave as radiation? Does it behave as matter? What does this mean? How does this move? Can we treat it as a fluid? Can we not? And then, is it a perfect fluid? Is it a non-perfect fluid? So all of these questions, like how do we consider them, are within the framework of thermodynamics, and therefore entropy is neither an input nor an output, but it is something, yes, neither an input nor an output, but it is something that we use and we rely on. And you can play around and see what would happen if you changed the laws of thermodynamics, if entropy wasn't constantly increasing, if gas didn't behave like a gas, and then you'd have to rederive a lot of what we assume about how things interact, but not just on cosmology, but in general. So short version of that, we don't need to put entropy as an input or as an output, but it is kind of part of the groundwork that is said. It's one of the things that we use to build up other things. So the fact that energy is conserved, the fact that an ideal gas will expand to occupy all of its space, and there's a relationship between the pressure and the temperature, these are things that we do assume. But these are things that are pretty well tested. So it's not something that we then see afterwards, like, oh, did we forget to include entropy here? Entropy is taken into account. Okay, hope that answers that question. That's a very cool question. I love questions about entropy because they always make my head hurt, to be honest. Like, I love thermodynamics. I've gone through thermodynamics hundreds of times, but sometimes it's thermodynamics questions that I'm like, cool. Yeah, I knew that someday. Has your desk moved? The view looks different. No, this should be my usual setup. I'm pretty sure things are the way they normally are. A poster behind me. That over there is the lamp probably in front of me. But I also feel like something's wrong and I can't figure out what. I spent the last 10 minutes staring around like something's just slightly off and I haven't figured out what. So technically my desk has not moved. The view should be the same as always. But yeah, maybe there is something off because I feel like something's off, but I can't. I think what's off is that my tea mug is on my right instead of my left, but you guys don't see that. So you don't know that my tea mug is in the wrong place, but I think this was what was perturbing me. Let's see if this fixes it. Okay, yes, now I'm happy with my desk layout. So no, my desk has not moved. Answer to that question. In the far future, after heat death or big rip, wouldn't that be lower entropy? So entropy always increases. By entropy, we mean the amount of order of a system or the amount of chaos. Yes, water is on one side, tea is on the other side. Everything is under control. In the far future, so heat death means that the universe has gradually expanded. Everything is further and further and further apart from each other. So it's so far apart that there's no interactions. But this actually means you kind of reach the maximum level of entropy because you have more chaos. So chaos is a lack of structure, a lack of order. If you consider my mug, okay, let's use my mug as the example. If I have a mug here that is in one state and I drop the mug on the floor, it is going to break. The one on the floor has more chaos. It has more possible configurations. There's many, many different ways you can rearrange those pieces, whereas the mug is a fixed structure. So once you break things down, you are breaking complexity and you are making things more chaotic. So you are increasing entropy. The universe likes being entropic. It likes having maximum degrees of freedom, which means maximum ability to be chaotic and disordered. So As the universe expands in the far future, you will have lower complexity and therefore you will be reaching maximum entropy. So universe expands, things gradually get further and further and further apart. And at that point, there's no exchange of information, no exchange of knowledge. There is no structure whatsoever, assuming Big Rip where everything gets ripped apart. Or if you just assume heat death, you will still have structures. They'll just be so far apart that they can never interact with each other. So even if you're heading to a heat death where the universe cools down, like the universe is going to cool down, whatever. The heat death means it gradually expands and expands and expands until everything is so far away from each other that nothing can interact. Big Rip, on the other hand, is where the universe is torn apart at its seams, where this expansion is so strong that it can actually overcome the fundamental forces and rip apart atoms. And at that point, you will reach practically maximum entropy because things are just gone. So Leonard Susskind has said that entropy is just the amount of photons or something like that. Really? Has he said that? I'm not surprised, but no. Entropy is not amount of photons. It's amount of information or amount of chaos or amount of order in the system. Yeah. So Leonard Susskind has some very good opinions about some topics. And let me cut that sentence off there. Okay, going back to the question, but conversations about entropy are very, very interesting ones, as mentioned. So continuing with entropy, because there was another question, and then I'll go back to the other question about Gaia and Milky Way and dark matter. Could entropy also be a field with values everywhere, just like the electron or Higgs field? Could entropy be a field? I don't think so, because it's a property you measure of the system, which of course you could say is also true for other things that are fields. So I don't think entropy could be a field, but I'm also not sure how to give you a convincing answer to that regard. So a field is something that has a value everywhere, like the Higgs field. Entropy is kind of the state of a system. It's not something that changes in one point or another. It's like if you take this room for an example, let's say this room is a closed system. At some point, you're going to have the same temperature everywhere in this room, but technically you could have tiny fluctuations and then an average temperature. But with the entropy, it's kind of about the room itself. It's like how much entropy is contained in this room. So it's not something that you really measure at a specific point. It's a property of a system itself. So I'm not sure if this makes sense to you, what I'm saying here, because I know this is... Yeah, entropy is more of a condition. It's a property that something has. It's not intrinsic to every part there. It's like this whole system has something that we call entropy. It's a property of the system. But yes, this is very difficult to explain. I'm sorry that I'm very bad at explaining thermodynamic concepts. I know it's something I need to explain better. But yes, entropy is about the system itself, not about these things inside, and therefore it's not a field, if that makes sense. If there's no Big Rip, but there is a heat death, would the matter decay, evaporate, and then end up similar to the Big Rip configuration? So it depends. Protons, for an example, may eventually decay. Neutrons may eventually decay if you wait long enough. So I think if you reach the heat death where everything has been pushed far, 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 far away from everything, and there's nothing for it to interact with, eventually maybe all the protons and neutrons would decay, and then you're just left with, well, protons and neutrons decay. Yeah, I'm not sure if everything would eventually decay, and I think it would be different to the Big Rip in the sense that the Big Rip would actually rip everything apart. It would rip all of the atoms away from each other, so you'd have no atoms together. Now, if you have things decaying, you might still have them decaying into smaller things, but I think that would be a much, much, much longer process. So you'd have to wait a very, very, very long time for that to happen. And some things are stable and will not decay because not everything in the universe does decay. Some things reach a stable configuration and stay that way. So the heat death would be everything is still in structures but very, very far away. Some of these structures gradually decay, whereas the Big Rip, everything is ripped apart and you have no type of structure left. Okay, keeping on the topic, would that mean that the early universe had the most possibilities because no structures had formed? Yes, in a sense, yes. But then it also had more heat and more energy. And yes, there is the interesting question of how do structures emerge with entropy. Seeing that entropy wants to increase, how do structures emerge? And that is a very interesting question. And entropy is so chaotic. Yes, yes, yes. What do neutrons decay into? I may have misspoke there. Let me just check one thing. A neutron decay. Do neutrons actually decay? Neutrons should decay. So yeah, free neutrons decay. Neutrons are stable once they're inside. Like in many nuclei, neutrons are stable, but they can actually decay. What do they decay into is a good question. The neutron decays into a proton and an electron. That makes sense. Okay, so that's what that decays into. Okay, so yes, sorry for the entropy questions being a bit weird. But yes, entropy is always decreasing, and then you can ask how do structures appear. But structures can also appear in a system where you have different. So the entropy is averaged over the whole thing, but you can have points where you can have structures forming, even though structures forming is an ordered process that is not favoring entropy. But then you've got something happening that is causing this structure to form. Usually gravity is happening or pressure is happening. So it's not a system that's been left alone. The idea is if you leave a system alone, entropy is going to gradually increase. But if there's something acting on this system, then you can change this. Okay, your entropy question led to chaos here. Yes, exactly. It often does. Chaos is a very entropy is a very complicated topic, and one that I am bad at explaining. But it does lead to very fun chaos and lots of very fun questions. Maybe we should all sit down, or I should sit down and do the research and like prepare this properly, and then we could do a whole stream about how entropy actually works. That could be fun. That could be fun. Maybe we can pencil in a whole stream. I'm gonna add it to my wish list of streams. There's some on there from many years ago as well. But maybe we can go more into entropy at some point in the future. Once entropy has increased, it could be noticeable enough to actually talk about it in the stream. Sorry for the very bad joke there. Okay. Going back to the idea here, data collected from Gaia recently point towards the absence of dark matter in the Milky Way. I have not heard about this. This is very interesting. Now, if you had no dark matter in the Milky Way, then you'd have to explain why every other galaxy that we've seen, or almost every other galaxy that we've seen, has dark matter, but the Milky Way doesn't. Why would the Milky Way be special in that regard? As far as we know, almost every galaxy we've seen in the night sky has dark matter. In fact, we believe dark matter is essential to galaxies forming. So if you don't have dark matter, it's quite hard to explain how the galaxy would be there. So if Gaia has indeed found hints that our galaxy doesn't have dark matter, then it's a question of why and how and what does this mean. I'm also not completely sure how Gaia is measuring that, because Gaia is within the Milky Way, and it's always a problem that once you're within the Milky Way, it's hard to measure what is happening inside your own system. And Gaia is not measuring dark matter. Gaia is infrared. No, which frequency does Gaia operate at? So Gaia is a satellite that is very cool. That is taking a lot of very cool data, and it is creating a three-dimensional map of the stars throughout the Milky Way. So I guess, yeah, if it's mapping the stars, and it can map the motion of the stars, and you can use that to compare to the prediction of dark matter. So yeah, Gaia is an optical telescope that was launched by the European Space Agency, and it is a successor to Hipparcos. So yeah, Gaia is mapping stars. And I guess by mapping stars, I have not read this paper, but I guess by mapping the stars, you could see the motion of the planets. Sorry, not the planets, of the motion of the stars. And from there, you can compare this to our predictions. So I was at a conference. This is related. I was at a conference this month as part of my crazy travels over the last couple of weeks. I was at a conference in Brussels. It's called News from the Dark, and it's a yearly event. This conference looks at basically what's new in dark matter, as the name implies. And this year there was like a big focus at the conference of galaxies and rotation curves. Yes, so they try to infer the shape of the rotation curve of the galaxy, and that the recent result for the Milky Way was a very classic Newtonian one. That is super interesting. I haven't read that paper, but that sounds super interesting. So the rotation curve, let's back it up here, and then I'll come back to the conference. When we look at how stars move around galaxies, we have a prediction. Like stars closer to the center of a galaxy should move faster, ones further on the outskirts should move slower. This is a typical thing of if you're on a merry-go-round, you feel a different amount of force if you're in the center or if you're on the outskirts. If you see a roller skate, someone on roller skates or ice skates, they put their arms up to go faster, they put their arms out to go slower. This is the same overall principle. It's angular momentum at play here. So what we expect when we look at how stars move in the galaxy is that the further away they are from the center of the galaxy, the slower they are. This is the standard prediction. However, what we've been able to see in pretty much every galaxy we've observed is that this is not the case. It seems that stars that are further on the outskirts are moving as quickly as stars that are close to the center. So this means that there's some other type of, this means that something has gone wrong here. The most common explanation is dark matter. If you have dark matter in a halo around every galaxy, so imagine galaxy is a disk and then you have a big sphere of dark matter. This dark matter is adding mass everywhere, and it means that things that are on the edge of the galaxy are actually still within the center of mass, or still within the mass radius. And so they're actually moving faster than you'd expect. So the idea here is that when we look at stars moving around galaxies, they move faster than we expect. And the answer that we have for this, or the most prevalent answer, is dark matter. So if Gaia has found that our galaxy, the stars move as you'd expect without dark matter, that is very, very interesting. So going back to the conference that I was at, News from the Dark conference in Brussels, we had a whole day dedicated to basically what is happening on galactic level. How does dark matter behave within individual galaxies? We have pretty good understanding of how dark matter behaves as a whole throughout the universe. So then it was the question of how does dark matter behave in galaxies? How do stars behave in galaxies? How does dust behave in galaxies? And how do we fit dark matter and all of this together? And there were some people at this conference who do not think dark matter is the solution. They think we've just misunderstood gravity on some scales. So there was some very interesting debate between modified Newtonian dynamics people and dark matter people, as myself. And my conclusion from a whole day of listening to people talk about galaxies is we have absolutely no idea what happens with galaxies at small scales, because we don't know how much we need to consider the dust of the galaxies. We don't know how much we need to consider individual stars and the bulk flow of stars and how stars move. So the general consensus was, yes, in general, on average, in galaxies, stars are moving faster than we expect. But when you get down to individual points here, it becomes very, very, very messy. I'm sure this was not everybody's takeaway from the conference, but that was my takeaway from a whole day of listening to people talk about galaxies, is that we have no idea about galaxies. So the question or the comment here was that Gaia has seen or has found that the stars within the Milky Way move in a way that is expected without dark matter. I have not read this paper, so I cannot comment on these individual results. If it's true, it's very interesting, because then we need to figure out what's different about our galaxy with respect to all the other galaxies. How did Gaia measure this? How much do we trust his results? So it is very, very, very interesting, and it definitely adds to the whole idea that there's something we're missing on galactic levels, because galaxies are messy. Did the debates between gravity versus dark matter explanations change your own opinion of how likely Jan's choice? No, it did not. It very much solidified my own opinion, mainly because I think the biggest piece of evidence we have in favor of dark matter is the cosmic microwave background radiation. Haha, made you wait 24 minutes for it today. Cosmic microwave background radiation, CMB, this is the oldest light we have in the universe. This is the afterglow of the Big Bang itself. And this is a snapshot of what the universe looked like 380,000 years after the Big Bang, or after the end of inflation. And by taking so what you see here is different, these particles of light from the from the time when they broke away from everything else after the end of inflation, and have been traveling since then. And the orange spots here correspond to ones that are hotter, the blue ones are colder. And by taking the statistical properties of these, we get a snapshot of what the universe looked like 13 point something billion years ago. Now, this picture here only makes sense with dark matter. If you try to explain the CMB without dark matter, you can't. And my question to all of the people working on MOND was, can you explain the CMB? And you get different types of answers depending on who you ask. There were some people who refused to answer this question. Some people who basically say the CMB is not an issue. We don't care about the CMB, which, I'm not going to react well to. But the general thing is that MOND is designed very much, modified Newtonian dynamics is designed very much to explain galaxy rotation curves. And it is very good at explaining galaxy rotation curves, which is this idea of how stars move. It cannot really explain the CMB, but people working on this will argue, well, it's not intended to. But then you need something else to explain the CMB. And the nice thing about dark matter is that it does both, and a bunch of other things. So my own personal opinion is that dark matter is a better fit to all of the data. That does not mean that we should stop looking into MOND, because it does lead to some really interesting results and some really interesting conversations. And if Gaia has indeed found that the Milky Way is moving different to what we expect, then that's new data that we have to consider as well. But coming at it from someone who's worked on the CMB many years, I think if your model cannot explain the CMB, then yes, maybe we are calculating gravity wrong. Could gravity be variable in ways we don't understand? This is basically what MOND people are saying. Modified Newtonian dynamics is the idea that we've misunderstood gravity, that there's something we're calculating wrong with gravity. But no model of modified gravity or modified Newtonian dynamics has been able to explain the CMB as accurately as dark matter. So, it depends what you prefer. If you want your galaxies to look perfect, or if you want the CMB to have an explanation and be able to be a useful data point. And I will always lean more towards using the CMB as the starting point and not something that you think about later. But they were very interesting debates, and they were all very good natured, and nobody got angry at each other. We all had an interesting time, and there were a lot of really, really cool debates and very interesting discussions to be had there. So, very long answer to that question, but if Gaia has indeed seen that stars in the Milky Way behave as they would without dark matter, that is really interesting, and that is something that definitely requires follow-up and thought, and it's something we should not ignore and not just say, like, well, galaxies, they're messy. And I find that this is often a problem that we have in cosmology and in astrophysics in general, is how dismissive people are of work that is not their own, or not just work, but areas that is not their own. And one example of this, yes, ironically, the absence of dark matter in some galaxies would also be a very strong argument against MOND, exactly, because then if we modify dynamics, we modify it for all galaxies, and then galaxies without dark matter or without this effect, then you need MOND to explain that as well. Of course, you need dark matter to explain that as well. So there is often the problem, I find, that cosmologists and scientists in general are very dismissive of work that is not directly their area. And the example that comes to mind is the Hubble tension. So the Hubble tension is this idea that depending on how you measure the expansion rate of the universe, you get different results. There's the number you get from the cosmic microwave background radiation, and then there's a number you get from local measurements of like Cepheids and supernovae. And these are more than 5 sigma apart by now, so it's a tension, it's a crisis, depending who you ask. But for many, many years, a lot of CMB people, their response to this was, well, the CMB value is correct, the others have probably made a mistake, or there's something we don't understand going on there. And I feel like this is sometimes slowing things down, right? This is something that perhaps nobody made Newton explain the CMB, so nobody should make me explain it. That is, in a nutshell, MOND. Yes, I'm sorry, but yes. So, yeah, I feel like this whole thing slowed the whole conversation of the Hubble tension down significantly, because to make the point here, the CMB measurement was very, very precise, and the other one wasn't. So people were saying, okay, we'll take it seriously when they do their homework and get it more precise, right? And now they have. So there's also this thing that dark matter people don't take MOND people overly seriously, and I know I'm guilty of this as well. And MOND people don't take dark matter people seriously. And this whole thing, there's this whole team of people working on galaxies, and we're like, well, galaxies, messy astrophysics. If something's wrong, it's in the astrophysics, right? And the astrophysicists will say if there's something wrong, it's in the cosmology. And there's this whole idea that people trust their own work but don't offer their fellow scientists the same amount of trust. Sometimes, not everybody. I'm not saying every scientist is guilty of this, but sometimes I find that this is annoying and might even be a hindrance. So I'm all for, I think there should be more cross-disciplinary research, even within the same discipline. Like people should know about different topics. And this is complete tangent here, but this is why I think it's so important for scientists to go to conferences and to go to seminars and to listen to people talk about stuff that is not directly their topic. Even if a seminar is off topic, going and listening is when you learn about what other people are doing. Having journal clubs where you can explore what is happening beyond your own field of expertise is extremely useful and should be done in a good way. Very long tangent there. A point I was trying to make here is that it's very easy for me as someone who works on the CMB to be dismissive of stuff that is galaxies. And I try not to be, but it is very easy to do. And at this workshop in Brussels, it was really interesting for me to see just how many different perspectives there are on the whole dark matter question. And people are approaching it from angles I've never even considered. And of course, there's no way I can say, well, the CMB should be your utmost starting point, and if you're not doing CMB, you're wrong, because who am I to say this, right? What makes the CMB a better probe than other things? Of course, I'm biased. I like the CMB. It is the best probe we have, but also people studying galaxies it's an equally valid approach to studying the dark matter question. So wrapping up this tangent that I just went on here, I think there should be more communication among scientists, and we should all be more open to the possibility that our own work might not be the best way of doing things. I love that some of them call it a crisis. Yeah, the cosmological crisis, the cosmological tension. Is cosmology in chaos? No, it's not. There's like a famous paper like Cosmology at a Crossroads, and it's all about these tensions, and it's dramatic, and yeah, it's very cool. So the Hubble trouble is about varying frames of reference with contradictory points of view. Pretty, yeah, to some degree. It's depending on how you measure the expansion rate of the universe, you get different answers, and that is perturbing because you would hope that you get the same answer and you don't. So now we're coming up with new ways to measure the Hubble tension or the Hubble value to see if we can shed some light on this whole debate. Okay, so I know there were a bunch of really cool questions that I missed because I was just giving very, very long answers to 2 or 3 questions. So we went on a long discussion about entropy, long discussion about Gaia. So we've basically done 2 questions plus follow-ups. Let's see what else. I know there was another question. So I'm just going through from the start and looking through everything again. So we did entropy. We talked about Gaia. Happy to take follow-ups on that. I didn't say hello to some of you who joined afterwards, but hello to everybody who's here. Okay, we did heat death, we did entropy, let's see. Then there was the question by Ben, what do you think about the discovery that faraway galaxies found by JWST have less heavy elements than closer galaxies? So that one is very, very interesting, right? Because I feel like JWST is finding a lot of stuff that doesn't seem to quite match expectations. There's also the thing that JWST has found stars that are brighter than we think, and it has found galaxies that are older than we expected. So there's a lot of stuff going on there. And let me just reread that question because I believe I read half of that and then missed the part that I should actually be answering. So where was that question? Yes. So faraway galaxies have less heavy elements than closer galaxies. Yeah, I have not read that, so I don't have a strong opinion about it, but I think it's really, really cool. And I think the information that JWST is bringing out is really, really interesting. And, you know, it's looking at stuff that is very, very far away, and it's not completely finding the expectation. In fact, we had the discussion 3 weeks on my last stream, which was 6th of September, many weeks ago, where Paul actually asked me about dark stars. These are stars made of dark matter. And the reason it's getting a lot of attention again, it's a model that's been around for 20 years. The reason it's getting a lot of attention again is because some of the stars that JWST has found seem to be in a different brightness than we expected. So then maybe there's something weird going on with dark stars made of dark matter, that the friction of dark matter is heating stuff up, which is a very cool idea. Wouldn't further away galaxies have less heavy elements because they're further back in time? Yes, that's what we'd expect, right? So when we look far away, we're looking far back in time. that means we're looking at younger galaxies, and these younger galaxies should have less heavy elements because they haven't had time for the stars to fuse their heavy elements, because we're looking at them as they were billions of years ago, not as they are today. So we'd expect that galaxies that are far away would have less heavy elements than galaxies that are close by. The comment here is that JWST has found the opposite. I have not read this yet. I have been very disconnected from science news the last few weeks. But if that is the case, it's very interesting, and then we need to ask the question again of why. It could be that JWST is going to challenge our whole idea of how galaxies form on the whole process here. But it does seem that JWST may have found galaxies that are older than we expected, galaxies that have more heavy elements, so that they're behaving differently to what we expected, stars that are too bright. There's a lot coming out, and I feel like the data we still need to sit on it for a bit and process it and go through everything that's happening. And I need to read the papers before I comment on them. But it's really interesting and it's really fun. So my answer to what do I think about it, I think it's really cool. I have no idea what it means in the grand scheme of our standard models of cosmology and galaxy evolution and so on. I thought JWST did just find that very far away galaxies that have less metals than nearer galaxies. That would make sense. But maybe it's found the question from Ben was the opposite. I haven't read the article, so I cannot comment on it. But, if JWST is finding stuff that is beyond what we expect, that's interesting. Anytime we find something unexpected, science progresses. You might suddenly figure out that everything we believed is wrong, and that is very, very cool. You might confirm what we know, which is also very, very cool. So I think it's definitely interesting, and we should pay attention to it, but I don't personally have much insight onto what this means because I haven't read the papers yet. Okay, so there was the other question here briefly of where was the conference? The conference where we discussed dark matter and MOND was in Brussels, in Belgium. It's the news from the Dark Conference, and it lasted 3 days, Monday, Tuesday, Wednesday. I was there for all of Monday, all of Tuesday, and I missed the last 2 talks on Wednesday. But it was really fun to go back to Brussels. I did my first postdoc in Brussels, and it was an interesting time because I lived in Brussels when pandemic hit. And it was nice to go back to Belgium in vastly different circumstances and just to see the city in a different light. Did not really change my opinion of Brussels, but it was nice to see it again. Okay, going back through the questions, and then I'll answer the latest one that happened that just appeared down there. Okay, going through, we did entropy, we've done JWST. Let's see, go through again. No structures returned. Yep, we covered this. Just catching up with the questions. You will keep thinking of new questions while I just make sure I've caught up with all of the other ones. Okay, Milky Way dark matter, can't we tell by the rotation rate versus total mass? Yep. So can we tell by the rotation rate versus total mass? The problem is we're inside the system, so it's quite hard to actually figure this out, because once you're inside the system, it gets hard. It's quite hard to actually do observations. It's much easier to look at things that you can actually see properly, but we are part of the Milky Way. So anything we do within the Milky Way will always clouded by the fact that we are within the Milky Way. That was related to how Gaia is measuring things. Okay. Okay, so if neutron is up plus down, quarks and protons are up plus down, does that mean up quarks release electrons when they convert to down quarks? That's such a difficult question. I'm going to say no. There is a weak force interaction. Weak force? Yes, I would say strong force. Weak force. There is an interaction happening. It's radioactive decay. Okay, it should be the weak force interaction here that mediates this and that changes the neutron when it decays into a proton. But I really cannot, off the top of my head, remember how that reaction looks like. So yes, funky stuff happens, but an electron is released. Or an anti-electron, one of those is released when a neutron decays into a proton, which is something that is on a very, very far away timescale for bound neutrons. Free neutrons can decay, but ones that are bound together don't decay too much. Going through your questions again, just making sure. I'm pretty sure I have missed some questions today, so if I have and I don't get to it now, please do let me know so we can go through it again. But I think that's all of the main questions up until this point, and now of course we're getting more coming in. So Trip question. Going to get to the trip question in a sec. So thanks, David, for stopping by. Always great to see you here. Always great to have you here. Trip question. Which of your destinations did you spend the least time in, and which the longest? Whew. So it was a whirlwind of a trip, really. So let's see. What did I do? I spent less than 48 hours in Germany. So my first stop on this trip was Germany to see my partner. That was less than 48 hours. So I think that's the place. Well, that's sort of the place where I spent the least. So it was 48 hours in Germany, so 2 days in Germany. Then 3.5 days in Brussels for the News from the Dark conference. Then I went to Montpellier for one night. So this was the shortest stop on the way. I was in Montpellier for basically 18 hours, which was long enough to get dinner, sleep, do a morning's work in a very cute cafe, and get on the train again. Then I was in Barcelona for 4 days. 4 days? Was it 4 days? Thursday, Friday, Saturday, Sunday. Yeah, 4.5 days. And then I was back up in Montpellier for a week. So Montpellier was short on the first night, but then I stayed there for a week. And then I went to Paris. Paris was less than 48 hours. So the shortest part of my trip was probably either the one night in Montpellier, which I'm not sure if you count. So then going from shortest to longest, it was the one night in Montpellier, then the weekend in Paris with my best friend, which was amazing, so much fun, and really nice, really, really cool weekend. And then going from shortest to longest, then it would be the weekend in Germany, then it would be Brussels for the conference, then the visit to Barcelona, and then the visit to my collaborator in Montpellier. So the longest part of my trip, where I stayed the most, was in Montpellier. I was in the second time. I was in Montpellier for 4 nights, and it was really fun. I visited someone who did his PhD at the same time as me in half of the same group, like he was between two groups. So we've known each other for many years now, and he's a good friend. And he hosted me in Montpellier for a week, so I got to meet the group. I gave a seminar, and the city is lovely. It was way too hot for me, but it was a really lovely city, and it was nice to just enjoy the Mediterranean, slightly like more north, but not quite Mediterranean, but still that kind of vibe. So that was very nice. And yes, the shortest part was probably the Paris trip, unless you count the one random night in Montpellier on the way down. But it was a lot of trains because I flew to Germany and then did everything else by train, like all the way down to Montpellier, down to Barcelona, then back up to Paris, and then flew home. So when I was in Montpellier, it was 31 degrees Celsius. I have no idea what that is in Fahrenheit, but it was 31 degrees Celsius, which for this time of the year was very hot. And more to the point, it was like double what it was back home, because when I left Helsinki, it was 15 degrees. And by the time I made it down to Montpellier, it was getting warmer and warmer and warmer, and suddenly it was 31 degrees. And it's too hot for me. But my week in Montpellier was really nice. I met some really cool people. Had a really good time there, actually. But the conference in Brussels, I feel like I learned a lot about dark matter. It was really fun because I've been working on dark matter for 14 years now? No, not that long. Let's count from my master's. So since 2015, 8 years. So I've been working on dark matter essentially for 8 years now. So so I've been working on dark matter for 8 years, and I think I've heard a lot of different perspectives. But it was really cool at this conference in Brussels to see that there was some perspectives that I'd not thought about, or some people who were really working on how dark matter behaves in galaxies. And that was really cool. And it was really nice to see so many different perspectives on the dark matter problem. And there were some really fun discussions. My only issue, I had a few issues with the conference. The biggest one was that everyone went over time. And I think if you're given a time slot, stick to it. You know, there's a small margin, but once you go over time, nobody in the room cares. Your voice is not more important than anyone else's. You asked Alexa to convert 31 Celsius to Fahrenheit, but then it kept leaning while you were talking and trying to answer things you said. Yeah, that's it's a problem with those things. But yes, 31 Celsius, 88 Fahrenheit sounds reasonable to me. Fahrenheit is a weird scale, makes no sense to anybody, but yeah, 88 Fahrenheit sounds reasonable. Just to confirm, you asked about JWST finding that faraway galaxies have less heavy elements. Okay, then I misread. Okay, then I misread. I thought you said they had more heavy elements. Yes. If it has less heavy elements, that is good. That is what we expect, right? That galaxies that are further and further away are older, and therefore they have less heavy elements because they haven't yet had time to fuse these elements. Okay, so this is what we expect. I completely inverted your question there. I was like, did it find this? Would be cool. But okay, if it did find something that is part of what we expected, then that's very cool. So galaxies that are far away have less heavy elements. This makes sense to me because they are younger. Therefore, they haven't had the further away it is, further back in time. So we're seeing the galaxy as it was in its infancy, and it hadn't yet had time for stars to fuse heavy elements, metals, as we call them. Anything bigger than helium is a metal in cosmology. So that makes sense. I had read your question and inverted it, but what you say makes sense. Yes. So JWST finding less metal or less metallic elements in galaxies that are far away makes sense according to what I think we know about, based on what I think we know about how galaxies work. How much is JWST part of discussions at conferences and among normal work interactions? Is there a feel of excitement or ominous feelings that science will be thrown into chaos? We do like chaos in science, don't we? But at least in my work, JWST is actually not overly relevant because I'm working on very, very, very early universe gravitational waves. Anything JWST finds or doesn't find will not challenge what we're trying to do with gravitational waves. And it's interesting for me from a dark matter perspective in case it finds weird things, but it's also not its main target. So I feel like JWST is extremely exciting if you work on galaxy formation and evolution or on exoplanets. It's a big deal. It's going to give us a lot of amazing data. But in my fields, it's not such a big deal, as in it's not going to change what we do so much. So it comes up occasionally at the News from the Dark conference in Brussels. There was a talk about JWST because we were talking about how stars behave in galaxies, and therefore it was relevant to bring that up. So yeah, it's something that I think is really, really interesting for a lot of people, of course, and it's going to give us a lot of information. It's going to really help us understand galaxies and exoplanets, and these things are really cool. But it's not really going to affect, or it's not expected to affect dark matter research, and definitely not early universe gravitational wave research. So while the JWST is exciting and it's a cool experiment that is badly named, but it's very cool that we have it, it doesn't really change much for us. One that we are much more excited about, at least dark matter people, is Euclid. So Euclid launched in June, 1st of July this year, and its mission is to measure dark matter and dark energy, basically. The Dark Conference, that would be a Star Wars fan conference also. Yes, it was called the News from the Dark Conference, but yes, the Dark Conference. So yeah, I think the one people in my field are much more excited about is Euclid. Euclid launched in July, and Euclid is set to map galaxies going back to 10 billion years ago. So it's looking 10 billion years into the past. And it's going to map galaxies throughout this time, like the distribution of matter, which means it's going to shed light on dark energy and dark matter. So what Euclid finds could be a game changer for dark matter research, or it could solidify our standard model of dark matter, which is also very cool. If Euclid doesn't find anything unexpected, great, our model is doing well. If it finds something unexpected, then we have to figure out what happened. So I feel like while JWST is an amazing experiment and creating its own news in different topics, it's not the overly relevant one for me. For me, the most relevant one right now is Euclid in terms of dark matter. Of course, in terms of gravitational wave research, we have to wait a few years to get one measuring stuff, but the pulsar timing array one was very exciting. So we know why dark matter doesn't interact with, do we know why dark matter doesn't interact with the electromagnetic force? Great question. Come to that in a sec. So to recap here, Euclid is going to give us amazing information about dark matter, dark energy. It launched in July. It's already taking data. It's set up. It's now doing the final calibrations, but we are expecting the very first data release not as far in the future as people think. I'm being vague. I'm not part of Euclid team, so I'm being vague. But I think there will be some Euclid announcement by the end of the year. Not actual data, but there will be something by the end of the year from Euclid, hopefully, or January, February, maybe. And then again, I'm not part of the team. This is not like insider knowledge, it's just rumors. So Euclid is going to be very cool in terms of gravitational waves. We had the pulsar timing array announcements, and now we're waiting for SKA and LISA, which will launch in 2013 something. Don't ask me the last digit, we don't know. Okay, do we know why dark matter doesn't interact with the electromagnetic force? This is a fun one to answer. And I would say because it's not charged, and things that don't have charge, electric charge, don't interact with photons, except the photon itself is not charged. So that's all. So yeah, the general idea is that dark matter does not have charge, and it just doesn't talk to photons in the same way. So not every particle feels the different forces, and the general idea here is that everything that feels the electromagnetic force has some type of charge to it, whereas dark matter probably doesn't. If it has, it's very small. It might be like milli-charged dark matter and have very, very, very insignificant interactions with photons. But then it's also just beyond photons, right? So it electromagnetically it doesn't interact with electrons either. So the Euclid announcement should start with Eureka. We found it. Probably not. I highly doubt that Euclid will find dark matter. It will just confirm or deny some of our existing models. Or not confirm. You never really confirm a model. It will just lend more weight to a model. So, why doesn't dark matter interact with the electromagnetic force? Because it doesn't have the right properties. It doesn't have needed components. It just doesn't see the electromagnetic force. And to answer it properly, we'd have to go in. So neutrons also don't interact with the electromagnetic force. See, I knew if I went with charge, I would be stumped with something. Yes, neutrons have negative charge. Neutrons do indeed interact with the electromagnetic force. Okay, so I'm going to have to think about a proper answer to that. For now, my answer is dark matter doesn't have the right properties to interact with the electromagnetic force. So it's something that we do know. Like, we don't know how dark matter was formed or what dark matter is. But in order to interact with the electromagnetic force, it needs to meet a certain amount of criteria, and it doesn't. As to how we define those criteria and what they are, let me get back to you on that one, because the answer you just gave was too hand wavy, and yes, doesn't completely work. So why does dark matter not interact electromagnetically? I will think about a proper answer to that. I'm writing down a lot of things like next week to give you proper answers to. We'll see how many of those I actually have time to look into. But yes, I feel like the question of why dark matter doesn't interact with the electromagnetic force, because it doesn't have the properties to do so, but why? That is a harder one to answer. But that is an excellent question. So sorry that I can't give you a good answer right now, because apparently my brain cannot come up with convincing answers to a lot of questions today. Okay, so another question here. Have we completely eliminated primordial black holes as being the source of dark matter? Absolutely not. So primordial black holes is the idea that you could have a black hole formed in the very early universe. So most black holes that we're used to are formed when stars collapse. Star reaches the end of its lifetime. Neutrons aren't uncharged, they have both positive and negative. Yeah, but then they cancel out and the net charge is zero. But I guess the components do have charge. Yes. Get into really like quantum physics stuff there. Okay, so primordial black holes would be regions of space-time in the early universe that are so dense that they can automatically collapse or directly collapse to form a black hole without going through the whole star formation process. Primordial black holes are hypothetical. They exist in many models of inflation. This is what we use to explain this period of exponential expansion in the early universe. But they are still hypothetical. We're not sure if primordial black holes exist or not, but a lot of people think they might. One cool thing about primordial black holes is, depending on how they're formed, they would have the right mass to be the black holes that are detected by gravitational wave experiments like LIGO, Virgo, and Cagra, where the masses for some of them are slightly off what we expected. And some people are saying, maybe we found primordial black holes. Cool thing about primordial black holes, if they exist, they could be a part of or even all of the dark matter. So you feel the same way about quantum mechanics. Yeah, quantum mechanics is fun. stuff. This is stuff that I absolutely should know because I am literally the teaching assistant for Introduction to Quantum Physics in a month. And I did it last year as well. It's fine, but when people ask me questions about, but why do things behave this way? It's like, I need to review some notes before the next stream and before my quest next month. But yeah, primordial black holes, stars, or sorry, not stars, regions of space-time in the early universe that could directly collapse into a black hole. If they exist, they may have been detected by LIGO and Virgo and Cargo, depending who you ask. And if they exist, they may be some or all of the dark matter. But there's a lot of uncertainty here. How are they formed? What do they look like? How do they behave? How long do they last? Do they evaporate? And depending on your answer to all of these questions, they may or may not be part of the dark matter. So it's a very interesting topic. And if you listen to some people, they'll tell you that primordial black holes are all of the dark matter. Other people will tell you that primordial black holes don't really fit. So we absolutely have not ruled it out as the dark matter yet. But Ant-Man movies use them like a syllabus. Yeah, definitely not relying on Marvel for any type of scientific accuracy. So primordial black holes are a really interesting topic and a very timely topic because people are talking about them a lot. And there's a very big community who think primordial black holes are the answer to the dark matter problem. It's something that we can explain. It's something that doesn't require many things beyond what we already know. And it would be an interesting solution. Other people think, well, if they existed, we would have seen them decay by now, and we haven't. So yeah, it's really, really interesting. We definitely haven't ruled out primordial black holes, but I think we definitely don't have enough information to say, yes, they are the answer. But one really nice thing about primordial black holes is, depending on, in the standard picture of primordial black holes are not compatible with the standard weakly interacting massive particle, which is the most common dark matter model that is searched for in collider experiments. And basically, the idea here is we haven't found WIMPs, weakly interacting massive particles, despite a lot of experimental efforts. People thought we would have found it by now. We haven't. Which then people are like, oh, is WIMP dead? Do we need to look beyond WIMPs? Depends who you ask again. But it's really interesting because in the standard models of WIMPs and primordial black holes, these two cannot coexist. Based on the way they're produced, they cannot coexist. Which means if you find WIMPs, you rule out the standard primordial black holes. If you find primordial black holes, you rule out the standard WIMP paradigm. Obviously, then you can evade this by changing some things in your model. But it's really interesting. And I think we're going to learn, I am expecting that we're going to learn a lot about primordial black holes in the future. In fact, one of the groups within the LISA Cosmology working group is basically focused on what will LISA, this future gravitational wave-based mission that I'm involved in, what will this actually tell us about primordial black holes? So there's a lot of people within the LISA team asking the question about primordial black holes. So they are absolutely not ruled out, and they are a very, very interesting dark matter candidate. So I'm expecting a lot more papers on primordial black holes over the next few years. It's a fun topic. If JWST is finding more or less galaxies, wouldn't that affect the number intensity of gravitational wave expectations in the universe and affect your research? So the galaxies themselves do not actually produce gravitational waves that will get in the way for me when I'm doing measurements, or not me personally doing measurements, but with LISA, because our biggest source of noise is supermassive black holes smashing together, which of course, if you have more or less supermassive black holes, that changes stuff. But galaxies themselves do not actually affect the gravitational waves. Of course, you could say if you have more, so LISA is going to mainly be measuring stuff within our own Milky Way, with the exception of supermassive black holes smashing together. Of course, you could argue if you have fewer galaxies, you might have fewer supermassive black holes. So then that could change the signal coming from supermassive black holes potentially. But I don't think it would be a substantial contribution. A lot of what LISA is going to measure is within our own galaxy, like galactic binaries, so white dwarfs in our galaxy smashing together, and then the ones that I'm interested in, which are these gravitational waves potentially produced in the very, very, very early universe. So if there are more or fewer galaxies, that the only way I could see that really affecting gravitational waves is via the supermassive black holes, of having more or less supermassive black holes smashing together. but I'm not sure how much that would affect Lisa predictions. So it's something that personally I'm not considering in my research, but maybe there are people who are considering how much that might affect the gravitational wave signal we could have. So that's a good question and a good thing to think about. If we know what black holes are and what white holes theoretically could be, what would grey holes be? Somewhere in between. It's fun, right? A black hole, everything gets sucked in. I know it's a joke, but black hole, everything gets sucked in. White hole, hypothetical, everything would be spat out. So what happens with the grey star? It's kind of that grey area in between. It takes things it likes, spits out other things. So yeah, it's. I feel like there is a duality for once. There is a binary. If you either suck it in or you push it away. It's quite hard to find a middle ground there. But then binaries are not a good way of describing the universe in general. So maybe someday we'll find a new type of black hole, white hole hybrid. But first we need to actually see if white holes are real. White holes are purely hypothetical for now. Okay, we have reached just over 1 hour. My voice is breaking quite a lot today. I think it's just because of the overall tiredness. So thank you, everyone. This has been really fun. You've hit me with some really cool and very difficult questions. I started today right off with entropy, which is always one that I struggle with. Why does dark matter not interact with the electromagnetic force? That's also on my list of things to check out. But we've had some really cool conversations and some fun tangents. And I like that you're all staying up to date with cosmology. Like you're asking me about JWST and about Gaia. These are things that are happening now. This is today's news in cosmology. And it's really nice that you're reading about this and think to come and ask me about this. It's really nice. Like, part of the purpose of Cup of Cosmology is to get people interested in science. And whenever any of you send me a news article or ask me like, hey, I saw this in the news, can you explain? To me, it means that Cup of Cosmology is succeeding because I'm getting you all interested enough that you look out for this news. And when you see it, you think of me and bring it back to the show or to ask me. And it just shows that people really are interested in these things. So I really do like that people ask questions about current news, about Gaia, about JWST, about Euclid, because it's great that you're all reading the science news and asking me these questions. And sometimes you hear about things before I do. Like I had not heard this latest Gaia result. Maybe it was mentioned and I forgot, but it's great that you asked me because then it reminds me that this is part of the purpose here, that everybody enjoys science. So thank you for these questions today. It's been really, really great fun. Stars are grey holes because they attract things with gravity and emit electromagnetic radiation. I like that answer. That's what a grey hole is. Maybe potentially we could write a paper on that. An April Fool's paper. We found grey holes. We call them stars. Anyway, after the last couple of weeks of traveling, technically next week, 8th of October and 15th of October, the next 2 Sundays, Cup of Cosmology will be on as regular, as scheduled. The weekend of the 21st, 22nd, I might take the weekend off because I have a major grant application that is due in 3 weeks. And I might take a few days off just to finalize a few things there, but that's all good. Next 2 Sundays, Cup of Cosmology should be on as usual. That is 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast, assuming no time changes. I know people change times at some point soon, stupid daylight saving time thing that we should not do. 7 p.m. if you're on the Central European summertime, 8 p.m. if you're in Finland in my time zone. So, Cup of Cosmology will be online next Sunday, same time as today. As always, thank you everybody for joining. It's been great fun, great to have you all here. Feel free to reach out to me on Mastodon. I'm DCHooper91_Cosmo. My Twitter account is I am gradually shutting down my Twitter account. So there are still Cup of Cosmology updates on Twitter for now. This is going to stop at some point. So if you want Cup of Cosmology updates, be sure to follow me on Mastodon or the YouTube channel. Reach out to me by email if you want, but my Twitter account is gradually being shut down. I am deleting all old posts, all everything. So get ready for the fact that at some point in the future there will not be Cup of Cosmology on Twitter. That's going to happen some point. Okay, thank you everyone for joining. This has been great fun. I hope to see you all again next Sunday, same time as today. And I hope in the meantime you all stay safe and take care of each other.